So, continuing with horizontal circles. Example 7. This shows a frictionless tabletop in top view. We're staring down at it. Mass is 4.15 kilograms. It's attached to a 2-meter long string, and it's moving at 2.5 meters per second. Write force equations and solve for the string tension. Okay? Which way would gravity be acting if we're staring down at this from the top view? Into the page. Is it sinking into the page? Is it flying out of the page? Kyle, you know what? I'm going to ignore gravity and the normal force because they cancel out. Here's what I'm really going to focus on. Nick, what path is this tracing out? A circle. Where must my net force be? Toward the... There's my free body diagram. What force is pulling me in a circle? The string? Or what's the fancy word for that? Not for a string. What's the fancy word for a string? Huh? Because what does this question ask me to find? Tension. In other words, when it says write force equations, here it is. Tension is what's pulling me in a circle. Which is nice. I got the T by itself already. Yay! There is no force pushing you outwards. There is not. Tension is going to be MAC, mass times circular or centripetal acceleration. I have 2 equations for A. Which one am I going to use? V squared over R or 4 pi squared R over T squared? Am I going to use this one? Or am I going to use this one? They're both on my formula sheet. Which one am I going to use? Why am I going to use V squared over R? Why is it, and I'm sorry to say it this blatantly, screamingly obvious that I'm going to use V squared over R? Because they gave me a V. 2.5. How would I know that I wanted to use the other one? They'd give me the time in period in seconds. Okay, it's meant to be, I can't call it a no-brainer, but it's meant to be, hey, McFly. Okay. Tension equals mv squared over r. Kevin, did they give me the mass? No, let's plug it in, 4.15. Did they give me the tangent speed, the circular the speed? 2.5. Don't forget the squared. Did they give me the radius? That's how long the string is. That would be the radius, right? There you go. What will the tension be in newtons? .968. You know what? If I go to 3 sig figs, I'm going to look there, and I guess the 9 is going to get bumped up because of the 6, so really 13.0? Yeah? Newtons. How many of you ever spun something on the end of a rope around your head? Okay, so you ready? Let's talk about some of the physics of that. Clay, if you spin it faster, what will happen to the tension? Yeah, which you know because you've tried, but there's the physics of it. See how the V is on the top? In fact, if you go twice as fast, what will happen to the tension? What's on that V? So if you go twice as fast, what's going to happen to the tension? 4 times bigger. If you go 3 times as fast, what's going to happen to the tension? 9 times bigger. Okay? Or a great example of this is the Olympic event called the hammer throw, which is a mass on the end of a string. And you may have seen in the Olympics, they spin and then they let it go. So if you could spin twice as fast, it'll go 4 times further because you've got 4 times the force on the throw, which is why they've really practiced that spinning. In fact, they brought it into shot put now. Shot put as well, they started adding a spinning motion, which wasn't done when I was younger. Example 8. A ball is attached to a mass, big M, by a string which passes through a hole in a frictionless surface. Hey, no friction, I like that. The ball travels in a circular path. Trav, what does this question want me to find? The what? Did they say speed or velocity? So that suggests to me, oh, you know what? Maybe somehow I'm going to get an equation with this v in it, and that's what I'll find. You with me? Well, any suggestions? What was that? No. Should have at least one approach we might try. Let's try doing a free body diagram. Since I have more than one M, I'll let the bigger mass be capital M and the smaller mass be... so let's do the easiest one first, the big mass. What are the forces acting on this guy? Get the obvious one, Dustin. So that's going to be big M, little g. What else? Yeah, it's a rope. Anything else? Nope. Not touching the ground or anything. It's not moving in a circle there. I feel better. I know I got one diagram right. I've been doing that one since grade 11. All right. Let's go look at the little mass. What are the forces acting on it? Get the obvious one. Well, there would be little mg down. Is it sinking into the table like quicksand? Is it flying off the table like Superman? So I think there'd also be a normal force. And since they're going to cancel out, I think, Raj, I could really have ignored them. I put them on there because I'm a nerd and they gave me a nice picture. What else? What path is this ball tracing out? A circle. So where must there be a force pointing? Toward the... So there has to be... Hey, what force is that? You okay with that, Trav? What did this question want me to find? And I said, I think I'm going to get that from the whole circle thing. Well, hey, what would the equation for that be? What path am I tracing out? What's pulling me in a circle? Who's winning? Tension. Except it's not going to be winner minus loser equals MA. It's going to be winner minus loser, no loser, equals MAC. Centripetal acceleration. In other words, Dustin, I think I'm going to say this. Tension equals MAC. Trav, what did you say they want me to find? I think then I'm going to say, I'll bring in the v squared over r version because that's got a speed in it. I don't know tension. Oh, but look. I know another force that must be the same size as tension. Which one? Kevin said gravity or mg. Which one? Big M. Because it implies that this is not going up or down, it's at rest, the forces on it must be balanced. So I think I can say for this guy, tension equals big mg, and I can now walk over here, big mg equals little m v squared over r. This idea of, oh, I know the winner's pointing towards the center, if you're clever, is really useful. How would I get the v by itself? What will I do with the little m? What will I do with the little r? Multiply, and how do I get rid of a squared? So if I hear you correctly, and I think I do, you're telling me the big M and the big G would drop down, there'd be an R next to it, there'd be a little m below it, square root, that equals V? Okay, I'm in. V equals big square root of big M, 0.036. That's what 3.6 times 10 to the negative 2 is, but that's less typing. G, 9.8, not negative 9.8. I took care of that all in my free body diagram. R, uh-oh. Wait a minute. Did they give me the radius? Ah, in the question. Whew. all over 0.009, because that's what 9.0 times 10 to the negative 3 is, but that's less typing. And I get 4.06 meters per second. Is that all right? Okay. Put your pencils down. Look up. So last day I assigned 1, 2, 3, 4, 5, 6, 7. Oh, I assigned all of them? Okay. No, I don't think, I didn't assign number 13, which is cool, but I didn't assign that. So, Mr. All of them, I don't know what you think the word all means, but that wasn't all of them. I'm going to start the next lesson. I'm going to go for another 20 minutes or so, and then I'll give the rest of the class to finish this stuff. But we just finished horizontal circles. What do you guys think the next lesson is going to be? Vertical circles, which is really cool, because now we can look at roller coasters and Ferris wheels that have loops. So, vertical circles, part 1. You ready, Mitchell? Yeah? For me? Quick look at Bunny, please. Person sits or rides on a Ferris wheel. Kohei, you with me? Good. They sit on a Newton scale that measures normal force, because that's what a scale measures, in newtons, not in kilograms. At the bottom of the Ferris wheel, what does the scale read? Does the scale read exactly mg, bigger than mg, or less than mg? You know what? Once again, this is a chance for us to vote. Once again, how you hold your hand up is how sure you got the answer. So, at the bottom of the Ferris wheel, in this position right here, if they're sitting on the scale, by the way, what does a scale measure? Okay, so really, even though I'm talking about a scale, which force am I really talking about? Okay, got that okay? That's why I got normal force here. Will normal force be mg, bigger or less? Who says A? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Who says B? No one? Who says C? You ready? You ready? Very simple to prove. And then we'll see if we can derive the answer partway through the proof. Kyle, you ready? What path is this person tracing out? Let's keep that in mind. This is a job for a free body diagram. What are the forces acting on this person? Get the obvious one. What path is this person tracing out? Where must the winning force be pointing? Toward the... What force is that? Does the normal force have to be bigger, smaller, or the same size as gravity if you're moving in a circle and you know that the winning force has to be pointing towards the middle? In other words, on a Ferris wheel that's moving fairly fast, because most Ferris wheels are pretty tame, but on a Ferris wheel you will feel heavier at the bottom. You'll feel like you're getting pressed down in your seat. That's not what's happening. It's the seat that's pressing up against you, but you'll feel heavier at the bottom. So, on a Ferris wheel, people feel light at the top and heavy at the bottom. Why does this happen? I've just proved the heavy. You know what? Let's prove the light. Kyle, what are the forces acting on this person on the top? Get the obvious one. What else? Pointing which way? What path is this person tracing out? Where must the winning net force be pointing toward? In other words, I know gravity has to be smaller. Has to be smaller. Oh, which means right now, all of you feel normally, no pun intended, that your normal force is mg. In a Ferris wheel at the top, you feel your normal force as smaller than mg. You feel lighter. Wait a minute, Mr. Duick. I put an fg. I wanted an fn there, didn't I? My subconscious was bugging me there. Sorry. Normal force is what you said, right? And I wrote fg. On the top, you'll feel lighter. At the bottom, you'll feel heavier. Now, that's on a Ferris wheel where your head is always pointing up. In a roller coaster, going in a loop, is your head always pointing up? No, in fact, your head is always pointing toward the... Okay, we'll tackle that next. But for now, have I convinced you just with the good free body diagram? Okay. And it all comes down from the fact that, Jason, if you're moving in a circle, the net force is pointing towards the winning force has to be pointing towards the... In the previous example, the Ferris wheel is a rigid, solid wheel. The top and bottom will always have the same speed. The motion is uniform. This is not always true. If I have a rope like this, and I swing it in a vertical circle, you can see at the top I'm slowing down a little bit because gravity is slowing me down, and then I accelerate on the way down. So we cannot look at a situation like this except right here and right here. To try and analyze this Mitchell like at a 45-degree angle or something like that, right now, that's beyond our skill. Okay? So, it says, consider a pendulum which will move faster at the bottom than at the top, like I just showed you. Write the force equations at the top. Okay, there's my picture. What are the forces acting on it? Get the obvious one. Gravity. What else? There's a rope. And this is kind of weird because tension is along the rope, and in fact, they're both down. What path is this pendulum tracing out? Where must my net force be? Toward the... So this is a trick question. Who's winning? What? I heard it. Someone said it. Both. Both. Right? It's going to be at the top... mg plus tension equals mv squared over r. Let's get the tension by itself. How would I get the T by itself? At the top, that's tension. Pardon me? Shouldn't I call it? I didn't hear you. He's saying the T and the T. I probably should, but you'll figure it out in the context. It's a good point. Hey, what about the bottom? Oh, and you know what? What I did do cleverly, Josh, was at the top I said this is going to be V1 because you're going a little slower at the top. All right. Hey, what are the forces on the bottom? Get the obvious one. Get the obvious one. Which way? Down. What else? Tension, and I'll draw it bigger because I know that the winning force is always pointing toward the center. So who's winning? Who's losing? This is going to be V2. How would I get the tension by itself? It's going to be mv2 squared over r plus mg. Just looking at those two equations, where is the rope more likely to snap? At the top or at the bottom? Why? because at the bottom you're adding mg, tension is larger. At the top you're subtracting mg, tension is smaller. And in hindsight that seems pretty obvious. Yeah, I think at the bottom that's when the forces are the great, but for what it's worth there's a lovely proof. So in a vertical circle there can be tangent forces that make the object speed up or slow down, like gravity. But here's the key idea. The net force is inwards, it's ma, or it is m4 pi squared r over t squared. And there's no horizontal forces. No horizontal forces. Yep. Yep.
Can you also calculate velocity by using energy?
By using energy? We're going to do that in a couple of lessons, so can you hold that thought? And the answer is yes, but it's a little more complicated because a lot of it depends on whether we're talking about a roller coaster where your head is still down or whether you're talking about a Ferris wheel where your head is pointing up and which way the normal forces are going. So the answer, yeah, we'll get to that. But it's a little more complicated than that. Okay? Hey, roller coaster. How do I know there's a roller coaster and not a Ferris wheel? Head's pointing down. Okay? A 70 kilogram passenger is moving at 10 meters per second at the top of an upside down roller coaster. Find the force the seat exerts on the person. What force are they really asking me to find here? If I say find the force that your seat is exerting, what force is that really? Normal force. Okay. Well, I got a picture. What are the forces acting on this person? Get the obvious one. What else? Got to be, since that's what they're asking me to find. Which way? Towards the center as well. I'll separate them just so they don't overlap. What path is this object tracing out? Who's winning? Ah, two winners. I can't say it's a tie. They're both winners, though, because one might be bigger, one might be smaller. But you know what? My equation, here's the important thing, is going to be normal force plus mg equals which version? Oh, m. Don't forget the m. Which version of acceleration am I going to use? Am I going to use v squared over r or 4 pi squared r over t squared? Do you guys understand how we're figuring that out? They gave me a speed. I'm using the one with the speed in it. If they give me the period, how long to go around once. By the way, at Playland, that's the one you'll use the most because that's easy to time. You need a radar gun to get the speed, or you got to calculate it somehow. Anyways, what does this question want me to find, Vikas? No. Oh, how to get the Fn by itself. Okay. M, 70, V, 10 squared over, where's R? Oh, in the picture, 8 minus 70 times 9.8. Minus 70 times 9.8. You get 189 newtons. Wow, that's nice. It worked out evenly. Well, I guess there's lots of zeros in there. That would make sense. 189, yeah? Sorry? Because it's not. You're not. You're accelerating downwards. There must be a force pushing you downwards because you're traveling in a circle and the net force has to be pointing towards the center. Hold that thought. Come back to it. Here's what you're really asking. Looking at this example, what would happen to the scale reading if the roller coaster moved slower? If this number got smaller, Fn would decrease. B, what if we sped up? So going to your question, Josh, it all depends on how fast you're traveling. If you're going really, really, really fast, you would actually feel heavier at the top still. You would feel like you're getting pushed into your chair upside down. But there is a speed, just the right speed, where this equals that, and then you would feel a normal force of 0. You would swear you were going to fall out of your chair, and you would scream, and you would grab the railings and be terrified. Okay? But if I go faster, then you'll actually feel, not that you're getting pushed up, you'll feel a net force pushing you down, and your brain will think, oh, it's because you're getting pushed upwards. Right? Because our bodies have backwards accelerometers. So faster, the normal force will increase. If you wanted to, for both of these, you could just write normal force equals mv squared over r minus mg. There's our proof. And then I would say as v gets bigger, as v gets smaller. Okay. This is really what Josh is asking. If the pendulum in example 3 or the upside down roller coaster in example 5 were moving at the minimum safe speed, what would that imply about the forces? Okay. Find an expression for the minimum speed. First of all, let's do the rope. So here's a vertical circle. I'm going to try and hit the minimum safe speed, and I want you to watch the rope very carefully. If I get to the minimum safe speed, what do you see in the rope? If it's slack, how much tension is there? I think the minimum safe speed would be if I could get tension to be exactly 0, bang on, no more, no less. Is that okay? So, now here's the equation that we derived. We did say we had tension and gravity down. We did say tension plus mg equals mv squared over r. But minimum safe speed, what's tension? So we get this. Oh, what else do I notice? Turns out the minimum safe speed doesn't depend on mass. And let's get the v by itself. How? Times r, and then? Turns out the minimum safe speed is the square root of g. For a rope. What about for a roller coaster? What do you think the minimum safe speed for a roller coaster is? When that equals 0. When you don't feel the chair pushing on you anymore. When you just start to enter free fall. In other words, hey, turns out, Josh, the minimum safe speed for a roller coaster is also the square root of g. I'm willing to bet ride designers, they would have that one memorized. You'd be saying, I want to make sure I have a healthy safety margin. What's the radius of my loop? I better make sure that when we get to that loop, I'm going faster than 9.8 times the radius square root. If you're going exactly that speed, you'll feel no weight. And, by the way, if you're only going slightly faster than that speed, you'll still be screaming because you're all used to the normal force being mg. The normal force would be way less than mg. You would swear that you were about to fall out of your chair and down into the loop. So they don't do that. You guys went on California Screaming? I think on that loop, even at the top, you feel like you're getting pushed into the chair. It's going fast enough that, trust me, the normal force is bigger than mg by quite a bit. Which also works, so that's a cool feeling too. If we spin a bucket of water fast enough, it's possible to momentarily invert the bucket and yet not have any water fall out. You've probably all done this as children or even as teenagers. You take out a bucket of water on a nice hot day, and probably, if you're like me, you've tried to push the envelope a little bit. You've tried to slow down. How slow can I get it before the water falls out? Okay. Why does the water not fall out? Well, what are the forces acting on a molecule of water? Get the obvious one. What else? Yeah, the bucket applies a normal force. Do you want to know what the minimum safe speed is? I've got news for you. It's exactly the same as this physics here, except it's not tension this time. It's a normal force. You want to know the minimum safe speed? Right there, when the normal force is 0. So, as long as V is bigger than V equals the square root of GR, we stay dry. Because that means, again, remember, Alex, your body is a backwards accelerometer. If there's a normal force, pushing on the water droplet, what it feels is that it's being pushed into the bucket safely. Right? Remember, this goes back to Vikas, your question already about, well, how come I feel like I'm getting pushed out? You're not. It's your own inertia. But that will mean there's enough inertia that the water will stay in the bucket still. Okay? And again, if you've never tried that, that's your homework this summer. Get a bucket of water. Hey, on a hot day, it's kind of nice to push the envelope, because if something goes wrong and you get soaked, that's all good too. Now we can start to look at when a car will leave the ground going over a curved ramp. Not a ramp that's curved this way, like just taking off a straight line, but when will it go fast enough? Oh, let's find out. A 72-kilogram student is in a car that's traveling at 28 meters per second. Let me just see, how much more am I doing here, Mr. Dewick? You know what? Let's finish this lesson off, and we'll get both done. Sorry, but... Okay? Yeah. Yeah. Okay. It says, when the car is at the top of the hill, what upward force does the seat exert on the student? Manny, just before you go, what is this question asking me to find? Which one, Captain Obvious? There's no such thing as an upwards force of the forces that we've looked at. Spencer, what? So look over at Manny and give him a little... Okay? So you ready? What are the forces acting on this car? Get the obvious one. Spencer, what else is there? Am I going to draw the normal force bigger, smaller, or the same size as gravity? What path is this car tracing out? A circle. Where must the winning force be pointing? Toward the... So am I going to draw the mg bigger, smaller, or the... normal force bigger, smaller, or the same size as mg? Smaller. In other words, you'll get that stomach feeling where you feel like you're flying out of your seat. You're not. There's still a force holding you in your seat, but you'll feel lighter. You with me? What's my equation going to be? Who's winning? Who's losing? Am I going to use m4 pi squared r over t squared or mv squared over r? Oh, they gave me the speed? Don't forget the m. What did Manny finally say that we were trying to find here? Well, let's get the Fn by itself. Plus this over at the same time minus that over, yes? I'm going to get a normal force of mg minus mv squared over r. And again, because normally you feel mg, you'll feel lighter because we're subtracting from mg. How much lighter? I don't know. Let's find out. M 72, G 9.8 minus M 72, V 28. Don't forget the squared. What was R? 120. You get 235.2, 235 newtons. Where normally they would feel 72 times 9.8, 705. This person's going to feel about a third of their weight. Okay, there would be, depending on who was driving, screams of fear or screams of excitement, depending on whether you were doing this deliberately or whether this was shocking. Okay. I don't know. I didn't grow up in Pitt Meadows. I know in Abbotsford, growing up there's 3 or 4 hills that everybody knows about, that if you take it just right, you'll get that feel. You won't leave the ground or anything, but you'll get that probably them out on the farm roads somewhere. Oh yeah, those dikes, I'm willing to bet some of those do it quite well. Okay. What would happen if we sped up? What would happen to the normal force if we sped up? It'd be smaller. So here's the next question. How fast would I need to travel for the student to feel weightless? What would the normal force be if I felt weightless? So really, we can make a little note here. Fn would be 0. So now it would be mg minus Fn equals, I'm just dropping down the same equation that we had before. But if the student felt weightless, Mitchell, what would the normal force be? Oh, and you know what else happens then? Would a little child and a fat person both feel weightless? See it? Now the mass only cancels now that I've canceled out the normal force. And I get G equal... Mr. Dewick, what? I'm getting V equals the square root of GER. Yeah, that's how fast you would need to travel. It's going to be the square root of 9.8. Was it 120? Yeah. .3 meters per second. Or about 123 kilometers per hour. What would happen if you went faster? You leave the ground. The car would, because now there'd be a net force pushing it away. Okay? If we went faster, we would leave the ground. Folks, please don't try that experiment at home, because all of you are dumb drivers. Raj has a mass of 72 kilograms. He's riding a Ferris wheel of radius 12 meters, and he's moving with a constant speed. Is he accelerating? Yeah, direction's changing. At the top of the Ferris wheel, the bench that he's sitting on applies a normal force of 450 newtons. Raj, what does A want me to find? Okay. Hey, Raj, this is a job for a free body diagram. What are the forces acting on you? Get the obvious one. What else? Which way, up or down? Am I going to draw normal force bigger, smaller, or the same size as mg? How do you know? Because we're moving in up, and the winning force always points towards the... Okay. And again, hopefully you've also noticed, Spencer, FC never shows up on my free body diagram. It shows up on the other side of the winner minus loser. It's going to be, for part A, mg minus Fn equals... And since they're asking me to find speed, what am I trying to... Oh, speed. You know what? I guess I could... well, I guess it's going to be times by r divided by m square root. That's not too hideous. V is going to be mg minus Fn, all of that times by r. Yes? And then divide by m. That would give me v squared, square root. I can do that. The radius is 12, bracket, 72 times 9.8 minus 450 divided by 72. Square root. You get 6.526867. That there? Double check me because I did a lot of typing. Is that right? Yeah? So let's go 6.53. Okay. Alex, back row. What does B want me to find? This is a job for a free body diagram at the bottom. What are the forces acting on the bottom? Get the obvious one. Which way? What else? Which way? Bigger, smaller, or the same size as mg? Sorry? Yeah. Oh, what's my equation going to be, Alex? That's kind of cool. mv squared over r plus mg, where the mass was 72. V, I'm going to write, Alex, 6.53 squared, but I'm going to use my answer button. R was 12 plus 72 times 9.8. And yeah, Raj, you're going to feel heavier at the bottom and lighter at the top. Nine hundred and 961 newtons. So we finished with our thought experiments. Sorry my lesson went long, but I wanted to get caught up. How many of you ever gone on a swing set? How many of you ever wondered if it was possible to swing so hard, so fast, that you could do a complete loop? Can a child do a complete loop on a swing set? Well, depends how you define it. Put your pencils down, look up. You guys haven't got the homework yet. Number 1. Number 2. Number 5. I skipped 4. Number 7. Number 9. Number 9 is a horizontal circle. 12. There you go, folks.